Okay, guys, I'm going to try this again now that I'm a little bit more familiar with this program. I am going to go a little quicker as I am limited to 15 minutes per video. So if you do need to review something, you can just back up and replay it. So what we're going to do today is learn about the mole. So the mole is basically a word that represents a number. In chemistry so far, we've looked at chemical reactions. We've learned, of course, the nomenclature reading formulas and the types of chemical reactions. And what we're going to do in this unit is learn how we can incorporate quantities into chemical reactions. So again, in chemistry, when we're looking at an atom or a molecule, of course, is a very, very small particle. And it's not really practical when we're doing chemical reactions to measure, let's say, one atom's mass or one molecule's mass. So we have to have a way of incorporating some kind of realistic way and something that we can measure and quantify and see when we're doing chemical reactions. So that's where the mole comes in. So the development of the mole concept, this is of course how we measure mass in chemistry. So just a reminder, the atomic mass that we see on the periodic table, right, is the average of all the isotopic masses, sorry, typo there, based on abundance, all right? So if you take a look at the periodic table, you can see that carbon has a mass of 12.01 units, which is the average of all of its isotopes. Currently, right now, masses of atoms and molecules are compared using something called a mass spectrometer. So I'm just going to show you what a mass spectrometer, how it works, although you're not required to know this for any assessments. It's just for interest's sake. So when you're using a mass spectrometer, the sample has to be put into a gaseous state. When the sample's put into a gaseous state, it enters the mass spectrometer where it's ionized. So of course, electrons are transferred, right? So you have positive and negative ions, which then move through a very strong magnet. The lighter ones are, deflected the most, and the heavier ions are deflected the least. And what you end up with is a graph that looks like this. So we can see the mass of the different isotopes of certain atoms, and of course then we can get the mass of them. Here's just a little cartoon, okay, who put my lunch through the mass spectrometer. All right, well then how does this relate to the concept of the mole? And this diagram sums it up pretty well. You can see here we have the mole. This is of course, the organism, the mole. So a mole essentially is equal to this number. This number is going to be very important to us, 6.02 times 10 to the exponent 23. So the mole, by definition, is defined as the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. So essentially, when we're saying the mole, it's how many atoms of carbon there are in 12 grams of pure carbon-12. All right, again, carbon was chosen so that it would give hydrogen a mass of approximately 1. And if you take a look at the periodic table, you can see that hydrogen actually has a mass of 1.008, pretty close to 1. There were masses based on other elements, but they found that by defining it by carbon-12, it works out to give hydrogen that mass of 1. And the number, so again, we're talking about the number equal to the number of carbon atoms in carbon-12. That number was determined to be this, 6.02 times 10 to the 23. We call that number Avogadro's number because of the contribution of Amadeus Avogadro to discovering that number. So therefore, this is the most important thing to take away from this. 1 mole of something consists of 6.02 times 10 to the exponent 23 units of that substance. So it's really important to remember that the mole is just a word that represents that number. And we often have different ways of using words to represent numbers. For example, we know a dozen equals 12 units. A baker's dozen equals 13 units. A pear is 2. And in chemistry, because we're dealing with such small entities, a mole is equal to 6.02 times 10 to the exponent 23 units. So to just give you an idea of how large the mole actually is, 1 mole of peas is enough to cover Earth and 250 more planets the same size as Earth 1 meter deep in green peas. A stack of 1 moles of pennies is tall enough to reach Proxima Centauri, the second closest star to Earth, and back again 7,448 times. A mole of marble spread over the Earth would cover it to a depth of 80 kilometers. If you owned a mole of dollars and spend $1 billion a day, then you could spend that amount per day for over 1 trillion years before you run out of money. Earth has only been around for 4.5 billion years. That's 0.45% of a trillion. So wow, and these are really small entities as well. A marble, a penny, these are pretty tiny things. And you can see how big it ends up being when we look at a mole of these entities. So to just give you an idea of how small atoms, molecules, and formula units are, I have a few pictures of samples of those things. Here is 1 mole of carbon. So 1 mole of carbon is equal to 6.02 times 10 to the 23 atoms. I'm also going to take this a step further. If you take a look at your periodic table, 1 mole of carbon is 6.02 times 10 to the 23 atoms. It has a mass of 12.01 grams. Hey, take a look on the periodic table. What does this say as the mass of carbon? 12.01 grams. Interesting. All right, here is 1 mole of H2O. Again, I would just want to point out one more thing. So 1 mole of carbon is 6.02 times 10 to the 23 atoms. 1 mole of water is 6.02 times 10 to the exponent 23 molecules. So the only difference here is I'm changing my unit, right? So when we're talking about 1 mole of carbon, we're just looking at the atom. When I'm talking about 1 mole of water, I'm looking at the number of molecules. So my unit is changing here, but again, mole just represents this specific number here. Now I want you to take a look. 1 mole of water is 18.02 grams. I want you to see if you can figure out where we get that number from, and we're going to look at that in our next lesson tomorrow. And again, the key to understanding the mole is that it always contains the same number of particles, no matter what the substance. All right, I'm just going to point out again, 1 mole of carbon was 12.01 grams. Try to guess how much 1 mole of lithium is. You're right, 1 mole of lithium is 6.94 grams. What about 1 mole of iron? You got it. 55.85 grams. So all of the masses on the periodic table is the mass of 1 mole of that element. Wow, pretty cool. So what we're going to learn how to do today is calculate the number of particles or the number of moles of a sample of matter. This handsome fella right here is Amadeus Avogadro. And again, the number 6.02 times 10 to the 23 is named after him. All right, before we get there into our calculations, we have to again specify what particles are. In chemistry, we basically have 3 main particles. We can have atoms, and that's if we're taking a look at something like carbon or perhaps hydrogen. Maybe I should take that off, and I'm going to show you why in a second. Carbon, I'm going to clarify, maybe iron. We can have molecules. Molecules could be something like H2O, right? It has to be covalent, or formula units. And formula units we use for ionic compounds. And there we go. For pure monatomic elements such as iron or copper, the particle is an atom. For diatomic elements such as oxygen and covalent molecules, so these are things that are covalent, we refer to them as molecules. And anything that's ionic, we refer to one positive, or sorry, I shouldn't say one, but we refer to the positive and negative ions and how they combine together as a formula unit. And here's just a picture to reiterate that. So here we have water, copper, and sodium chloride. So if we're looking at a sample of water, we're talking about the molecule, which is one H2O. If we're talking about carbon, we're referring to the one atom in that sample. And if we're referring to an ionic compound, we're just taking a look at the positive and negative ions and how they combine together. For sodium chloride, we have one sodium combining with one chlorine. But of course, we know that they end up combining all together to form those crystals. Again, 1 mole of water, 6.02 times 10 to the 23 molecules of water. 1 mole of copper would be 6.02 times 10 to the 23 atoms of copper. And 1 mole of sodium chloride is 6.02 times 10 to the 23 formula units of sodium chloride. So again, to reiterate, the unit can change. We can go from something like trees. 1 mole of trees is 6.02 times 10 to the 23 trees. We can go to atoms. 1 mole of helium refers to atoms. Then we have covalent compounds. So 1 mole of a molecule is 6.02 times 10 to the 23 molecules. And also formula units for ionic compounds. So 1 mole of lithium nitrate, for example, is 6.02 times 10 to the 23 LiNO3 formula units. Now we do have a nice little formula for converting moles and particles. So little n represents moles, uppercase N represents the number of particles, and Na represents Avogadro's constant, which of course is 6.02 times 10 to the exponent 23. So we're going to go through a few examples. The first one here is how many moles of sodium bicarbonate are there in a sample that contains 3.89 times 10 to the 24 formula units. So I'm going to annotate here, and I'm also going to write my Gibbons list, which is really important in chemistry. So we're looking for the number of moles, N. And we're given a sample that contains 3.89 times 10 to the 24 formula units. That tells me I have an ionic compound. Sodium bicarbonate, of course, is ionic. And that's represented by an uppercase N. Now I know my formula is little n is equal to N over Na. I know Na is a constant. It's always 6.02 times 10 to the exponent 23. The only thing is I have to make sure I use the right unit here. Because we're dealing with ionic compounds, this one's going to be formula units per mole. And now I'm ready to sub in. So N is 3.89 times 10 to the exponent 24. Sorry, this is a little bit messy because I'm using my laptop. I'm just using form units as a short form, divided by 6.02 times 10 to the exponent 23 formula units per mole. Now our unit analysis, the formula units cancel. I'm left with units of moles, which is what I'm looking for. Oops, sorry folks. And if I go ahead and calculate that, what I'm going to end up with is 6.46 moles. Now, this is really important for using our calculators. When I'm typing in 3.89 times 10 to the exponent 24, this is what you type on your calculator, 3.89 exp 24. You don't have to type in the times 10. What ends up happening if you do that is that it actually gives you one more decimal place. and you would divide that, by